Okay, this is Professor Logue. I wanted to talk now about network protocols. What are they and how do they work before we get into how to administer a secure network? So that's the first learning objective. These are the slides from this particular topic, Unit 7 in your Cengage textbook. So first off, these are the objectives overall. We're going to focus in this screencast on this very first objective, which is the functions of secure network protocols. In subsequent screencasts, we'll look at the placement of security devices and the technologies that are used, how we can analyze security data that's coming from these security devices, and then lastly, how to manage and secure network platforms. But here, the focus will be on secure network protocols. So this is a quick review, hopefully, for you on the secure network protocols that are out there. Why do we have them? Well, these are rules for communication, and this goes back to the very start of the internet. The idea being, how do we get computers that have different operating systems to communicate with one another remotely? So this was developed by Dr. Robert Kahn and Dr. Vinton Cerf. It's the so-called suite of protocols known as TCP/IP, or Transmission Control Protocol Internet Protocol. As it says here, this is the most common protocol suite for LANs, local area networks, and the internet as a whole. It's a suite of protocols, so that means there are a bunch of them that all interrelate. And what you see down here are the various conceptual models. The first model is the OSI, or Open Systems Interconnect model layers. And these are the 7 layers that you remember, and there are 2 mnemonics. All people seem to need data processing. If you go from the top layer down to the bottom layer, if you go the other direction, it's please do not take salami pizza away. So this is the conceptual model. An implementation of that is this one, the TCP/IP protocol architecture layers. You can see that the application, presentation layer, and session layer are essentially combined in this implementation protocol and referred to as the application layer. The transport layer maps to host transport layer, the network layer host to internet layer, and lastly the data link layer and physical layers both map to the so-called network interface layer in the TCP/IP model. In this far right object here in this diagram, you can see the protocols that are in play at the various levels in the hierarchy. So down here at the bottom layer, you can see such things as the Ethernet, token ring, frame relay, ATM. These are the protocols that were developed to handle communications at these lower levels of networking. On top of that are these particular communications protocols. The address resolution protocol, you're familiar with that. We've talked about it, the internet protocol, and then these others as well. At the transport layer, we have the TCP and UDP. We'll talk more about this and get some experience using these as we move into the follow-on courses in the cybersecurity matrix. In particular, the 163 and 164 courses. And then at the application layer, you can see a whole plethora of protocols. Each one of these is focused on a particular application, specific purpose or function for us humans at this top layer. So some of these you should be well familiar with already. Hypertext Transfer Protocol, the language of the web, Post Office Protocol for email, and so on. So we'll take a quick look at each one of those and discuss a few things about them. IP, again, is that internet protocol, and this is operating at layer 3. This is where routers live. This is functions primarily at that layer, and it provides the essential networking, addressing, and routing capabilities. Again, this is where routers live. TCP, this is up one level at layer 4, transport layer. This is enabling communications via connections is the watchword here. Connections. We're managing connections at the transport layer. The protocol that does that is TCP. When we do the 164 course, when you take the 164 course, you'll be able to look at the IP and TCP headers of every packet and see how these things are interconnected and piggybacked on one on top of the other. TCP/IP actually uses this four-layer architecture known as network interface, internet transport, and application, right? So that's what you saw on the last slide. So here's a depiction of that, once again, simplified drawing showing the OSI model versus the TCP/IP model. This is the kind of thing that you might get asked in a job interview, to compare and contrast these two models. So the last slide in secure network protocols is looking at how they relate to security. What are the ones that are associated with that directly? Well, we have the SNMP. This is the Simple Network Management Protocol. Over the years, this has had several security backfits on it to make it more secure. The domain name system, this is a workhorse functionality of the web. And then lastly, file transfer protocol. All of these started out with simple versions where security was not a focus, but now they have been made secure through backfits and in some cases complete redesigns. So as it says here, there are also email protocols in addition to these that aren't secure. We'll talk about a few of those and the steps you can take to protect email correspondence. So let's take a look at this first one, SNMP. What is that? That was introduced back in '88, and as the name implies, it's about managing, there's an M there, Simple Network Management Protocol. And every equipment manufacturer needed to support this protocol. So it allows, what does it do? It allows administrators to remotely monitor, manage, and configure network devices. How does it do it? By exchanging management information between network and devices. To make this happen, every device has to have loaded on it an agent or service that can accept the commands sent remotely for managing the network and then executing them. So what are some of the devices? It's listed here: switches, routers, hubs, and so forth. But it's not just those obvious ones. You also have printers, copiers, fax machines, and even UPSs that could have a SNMP agent on it. The information is stored in a management information base. This is the database that has the particular values of the attributes that allows an SNMP device to communicate using this protocol. So how does this work? Well, these agents are password protected using something called a community string, another name for the type of password. There are two types of these community strings. You can have a read-only string or you can have a read-write string. And as the name implies, the difference is read-only allows information from the agent to be viewed but not updated or changed, whereas read-write does allow the data to be changed. So this then forms the basis for some potential security vulnerabilities. And the previous versions, 1 and 2, were susceptible. They had these vulnerabilities. So along comes version 3 in 1988, which is the latest version that uses usernames and passwords along with, and this is what makes it secure, encryption, using encryption so that these are less easily hacked. So first, the default SNMP community strings for read-only and read-write were called public and private. And the problem was they were transmitted in clear text even in version 2. So the vulnerability was that an attacker, all they'd have to do would be to put a Wireshark protocol analyzer, for example, in that network, and they could see the contents of these strings as they were being transmitted. So those are the key issues with SNMP you should be aware of. That takes us to the next protocol, domain name system. The domain name system deals with mapping IP addresses to their symbolic name, or as it says here, FQDN. That stands for Fully Qualified Domain Name. So for example, if I wanted to find the address of google.com, I could do an NS lookup to find that, and that would use the domain name system to resolve this symbolic name into an IP address. How does it work? Well, it's a distributed database organized in a hierarchy. How does this work? Well, first off, the database contains records that consists of the name of the site, whatever the web page is, and its corresponding IP number. So it's like a huge Excel spreadsheet. You can think of it that way. And it's just, like I said, it's distributed to many different servers on the internet. Why would you do that? Why don't you just have one place? Well, obviously that would not be good. That would then become a huge choke point, or what we would refer to as a single point of failure in fault analysis. If you took out that server, boom, down comes the internet. So we have a distributed database so that there are installed backups to prevent bottlenecking and ensure efficiency. So here's an example on this slide that shows the DNS in normal operation. Here's our requesting client, and you can see there's like 5 steps here involved. And this client is trying to go to this web page, www.nashville.com. So the first step is the local DNS server. You saw this in the topology lab early in the semester. So it knows the IP address of the DNS or root DNS server, which is down here. So it's listed in here. So it asks that question first. If it doesn't already know, it asks this question: what is the address of the COM server, that top level domain? So this root DNS server doesn't have the ultimate answer. So what it does is it helps the process along the way by resolving this first part, the COM server. So you can see it has COM, EDU, MIL, and a bunch of others, and it says, well, I don't know, but here's your COM IP address. You can ask them. So that address is sent back, and then there's a subsequent lookup to that address that you can see right here at the so-called top-level DNS server. What it has in its database is not the ultimate answer, but it has the addresses for Nashville, Microsoft, and Atlanta. And it says, well, I can give you part of the answer. So it looks up Nashville and finds this dotted quad associated with the Nashville IP address. So it sends that back. It actually takes this value here and sends that back to our local DNS server, and finally goes to that like local post office, if you will, and asks from the authoritative DNS server, authoritative, meaning it has the final say, if you will, on what it is. And it looks up the specific value, and it does have that in its database, so it supplies the 158.24.3.9 back here and then back to the browser. So this is often seen, the domain name system is a particularly lucrative target for potential hackers. So it has become a focus of attacks using several approaches. One is DNS poisoning. This is basically polluting or substituting or replacing a legitimate IP with a fraudulent IP in these databases. And there are several ways it can be done. It can be done in the local host table or in the external DNS server like you saw on the last slide. How do you prevent this from happening? Well, remember I said there were backfits. Here's one. This is the domain name system security extension DNSSEC. This is not actually a backfit. It is like a new design for DNS. It adds additional resource records and message header information that actually does some authentication to make sure that you're getting who you think you're getting when you're resolving DNS, when you're doing DNS resolutions. So an attacker, another approach besides DNS poisoning, an attacker can ask a valid domain name server for a zone transfer. Zone transfer is a normal capability of the web, but in this case it gives valuable information to the attacker and allows them to access network, hardware, and operating system information. So let's move on to FTP, File Transfer Protocol. This one has had some security vulnerabilities as well, and there are 2 potential fixes here. There's a backfit and there's a redesign that we'll talk about. So TCP/IP protocol is used for transferring files. By itself, FTP is an unsecure protocol used to connect to a file transfer protocol server. You're just moving files back and forth on the internet using this protocol. So how can you do it? Well, this is what you see most often. You can do it at the command prompt by typing in an FTP command to send a file from your computer, say, to a remote computer. Or, a lot of people don't know this, you can actually use a web browser. It supports not just HTTP, but also FTP. Or, then you actually type this into your browser. Or, you can use an FTP client, an application that has maybe a GUI that allows you to conduct these transfers via a window-based GUI application. So here's one of those, the FTP client called FileZilla. So you can see here's the GUI that allows you to do these transfers. So you can see it's kind of split into two halves. On the left side you can see the local site. On the right side you can see the remote site. So this is your local computer and this is your remote computer, and you can see the file hierarchy in each one of those. And then it's kind of like a drag and drop. You can see down here where we're actually moving files. So how does it work? Well, behind a firewall you got some challenges. First of all, it needs two ports to work, port 20 and port 21. It's important to remember which one is which for your CompTIA certification exam. So port 21 is for control, establishing the connection, terminating the connection, but port 20 is where the information actually flows. It has two modes, active and passive. The client's firewall can sometimes drop packets on port 20. Remember, that's the data connection. And in passive mode, the client actually sends a special command called PASV to the command channel, and the server responds with a port number to establish the data channel when you're in passive mode as opposed to active mode. Alright, so this is an example of active mode. You can see the client computer here on the left and the server computer on the right. And you can see the two channels of communication, the two ports. This is port 20 down here, which is the data connection initiation, and this is port 21, which is the control connection. So in this process, the FTP client initiates a session to this server by opening this command channel first. This is a command channel connection to the server on port 21 to request the file transfer, and it sends a port command to this server. The server will then attempt to initiate the second line of communication, the data channel, back to the client, this time on port 20. But again, with the firewall, the client's firewall may see this second data channel connection request from the server as unsolicited and drop the packets. This would break FTP in this case. So to avoid this, you can set up your FTP service using what's called passive mode that we described on the last slide. So in passive mode, what happens is the FTP client, that's again on the left, initiates the session to a server by opening a command channel to the server's port number, again on port 21, requesting the file transfer, sending the port command to the server. But in passive mode, the client initiates the data channel connection as well. So this is going the other way, as different from what we saw in active mode on the last slide. So the client now is the initiator for both communications. And how does this happen? Well, it sends this passive PASV command on the command channel, and the server will respond with the TCP port number to which the client should connect to establish the data channel. So that could be something else. You don't see a 21 down here like you did on the last slide, and it's typically a port number between 1025 to 5000, a higher port number. So what are the vulnerabilities of FTP? Doesn't use encryption. Subject to the man-in-the-middle attack. If I can get in the middle there as a hacker, I can read these things that are coming back and forth because it lacks encryption. So what are the fixes? I said there are two. One's a backfit, one's a redesign. So this one can be considered a backfit. The way to remember that is the S is tagged on the end, backfit. So it uses a secure socket layer to encrypt the commands. So it's the existing FTP riding in this secure sockets layer, SSL or transport layer security, to encrypt the commands sent over the control port. So that way the data port, and in this case the data port, may not be encrypted. a better solution that's designed from the ground up, the so-called secure FTP, so the S appears in front as opposed to in back for the back bit. This uses only a single TCP port instead of two, and everything is encrypted, unlike the FTPS. All right, so let's move on to our last one, which is secure email protocols. We have the Secure/Multipurpose Internet Mail Extensions, or SMIME. This is a protocol for securing email messages, and it could include embedded graphics or audio clips, multimedia. That's why it's called multi-purpose. And to be able to use this, though, the browsers have to be able to support these other protocols. Of course, nowadays they all do. What are the limitations with this secure email protocol? Well, it can't be used when mail is accessed through a web browser. You have a lot of web-based email clients these days. So you rather need a dedicated email application, something like Microsoft Outlook that's not web-based. Because SMIME encrypts the entire message, this makes it difficult for third-party tools then to inspect the email for malware. So that's a limitation as well. Because it would be encrypted, you can't look inside, you can't see the malware. So what is the solution to this? Some enterprises and government agencies like DISA, for example, they automate the process of encrypting and decrypting emails so that they can have access to that. And to do so, they use what's called a mail gateway appliance. So you can take a look at some of these examples in your textbook of examples of mail gateway appliances that could be used for this purpose. So let's take a look at the last slide here, network protocols. In the first column you have application or technology, and in the second you have recommended secure protocol. So for each of these applications you can see the secure version. So it's important to know to be able to map this in your head. In most cases it's pretty straightforward. You get an S somewhere tacked on to indicate that you have the secure version. And in case of DNS, it's actually an extension, DNS security extensions. Okay, if you have any questions, please send me any questions either showing up in office hours or via Canvas chat.